Managing the interaction force between the catheter and the surrounding environment is important to avoid tissue damage. The catheter may contact with vessel walls during interventions. Note that in this case, the catheter is forced to bend, so an interaction force is applied on the tip. The EM sensor will measure the tip position and then send it to the control STM network. The network predicts the pressure that can advance the catheter tip to an appropriate position, and in this position, as the catheter is bending actively, the interaction force is minimized. The algorithm was validated on a pneumatically driven catheter system. The input pressure is regulated by a pressure valve, while the tip position could be measured by a laser distance sensor or an electromagnetic sensor. We use different descending sinusoidal pressures to excite the system and generate training data for the control STM. The control STM is trained with data collected in free space. Within this work, a 4-layer stacked control STM was established. The hyperparameters such as number of layers or number of neurons in each layer were derived from an ablation study. We showcase the ability of the control STM in compensating the hysteresis and is able to be used as an open-loop position controller. We have tested the performance of the control STM on 4 trajectories that contains diverse patterns. For comparison, we implemented a sophisticated analytical hysteresis model called Inverse Deadband Rate-Dependent Prent-Ishlinsky model. The results showed that the control STM is capable of controlling the catheter tip with a sub-degree precision while robust to severe hysteresis. The control STM outperformed the inverse DR-DPI model by at least 75% in 4 test trajectories. The compliant motion controller is first validated in a simplified setup with the interaction force measured by a force and torque sensor. In the first experiment, the contact was made at the tip of the catheter. First, we turn off the compliant motion controller. One can see that the contact force increases as the tip is forced to bend. Now we switch on the compliant motion controller. And now you can see that the catheter bends to almost the same position as in the previous test. However, the interaction force was reduced a lot and always remained at a low level. In the second experiment, the force was applied in the middle of the catheter. The left one shows the compliant motion control is switched off. The right one shows the controller is in operation. The interaction force is significantly reduced with such a compliant motion controller. The results show that the catheter stiffness can be reduced by around 70% with such a compliant motion controller. The proposed compliant motion controller is further validated in an aortic phantom. During insertion, when the compliant motion controller is off, the catheter has to be retracted and reinserted in order to pass some areas. The catheter is finally stuck in the aortic arch with its tip directly puncturing the vessel wall, therefore causing a large interaction force. On the contrary, when the compliant motion controller is in operation, the catheter tip bends to reduce the interaction force and moves smoothly until reaching the aortic root. During retraction, as shown by the video, the catheter can even not be retracted without the compliant motion controller. When the proposed controller is running, the catheter can be retracted very fast without causing large interaction forces. The results show that with the proposed compliant motion controller, the maximum interaction force can be reduced by 71% and 40% during insertion and retraction respectively. Thanks for watching.